Hello, Dr. Huan here. In previous lesson, we talked about the informal definition of limits, and we looked at a few examples, how to find limits graphically, numerically, and looked at the scenarios where limits doesn't exist. And we even discussed whether table is trustworthy or not when we find the limits, right? So today we are going to talk about the formal definition of limits. It's okay to skip this lesson. However, if you're a math major or you want to dig into the definition of the limits, I encourage you to go through this lesson and at least do one proof problem. Now, let's quickly review the definition of limit, informal definition of the limits, okay? Suppose f is defined for all x near c except possibly at c. If f of x is arbitrarily close to L, as close to L as we like, by taking x sufficiently close on either side of C to C, we write this, we use this notation. Now, let's read this carefully. So, when you say if f is arbitrarily close to L, how close? As close as you like, okay? But you will have to tell me a quantity so that I know how close you like, right? So it's arbitrarily close, but how close? We need a measurement. So therefore, you will have to give me a quantity, how close that you want it to be. So let me write this down here. So you tell me that you want f of x within certain quantity. So, but this quantity is arbitrary. So you're going to say any quantity. And by the way, this quantity, we're going to use epsilon to make it general to represent this quantity. You can name this quantity this epsilon any quantity. You can say 0.5, you can say 0.01, 0.001, etc. Depending on how close you want the f of x to be, okay? Then, well, within certain quantity of L, okay, of L. So L within certain quantity. Then here's what I would do. I have to convince you that this can be done by taking x sufficiently close to C from either side. Then that means in order for me to convince you that the limit is L, then I will be able to find U a value, another value different from the epsilon, and this value actually we are going to call it delta, okay, the delta, not 8, sorry. So the delta, the Greek letter delta, so that and this delta is around the C, and if x is within that range, okay, within that range, the delta range, basically around the C, basically that means x minus C is within this delta quantity, then f of x is as close to L as you want it. So this is essentially what it means. So you tell me how close you want the f is to L by telling me a quantity epsilon. Then I should be able to find U another quantity delta so that this x is within this range of C, the delta range of C, which means sufficiently close to C. Then this y value, my function y value will be within the range to L as you wanted. If I can do that, then that's how I prove that this limit of f of x when x is approaching c is equal to L. Again, because this quantity that you provide to me will be arbitrary, so it's as small as possible, and I can always do that. That's how we prove that. Okay. So now let's actually use one example to start with one simple example to show you how this actually works. Okay. So consider this function. This is a simple function. It's a linear function. And the limit when x is approaching 1, f of x is equal to, so you can build a table or you can make a graph and then see that it's actually 10. Okay, it's actually 10. This is what we want to show. We want to show that if f4x plus 6 is arbitrarily close to 10, as close to 10 as we like, by taking x sufficiently close to 1. This is, if we are able to show that, then that tells me the limit is 10. Of course, like I said earlier, how this works is you will challenge me by providing a quantity epsilon, and then I'll take your challenge. If I'm able to find a value delta to make that happen, so that x is within this delta range around c, f of x is within the range around L, epsilon range around L, then I do my job. Okay, then that's enough evidence to conclude that. So now let's begin by picking an arbitrarily small number. Okay, so let's say, of course, later on we'll make it more generic. So for now, let's make it concrete. So you are going to give me a small number. That's your close, how close you want the f of x close to the limit L. So let's say 0.01 in this case. Okay. So it's really just arbitrary number. You can say 0.5, you can say 0.001, or you can say 0.00001, any small number that you can think of. My job is depend on this number that you provide to me. I'll find you another delta so that your the y value will be within the range that you wanted, around the 10. So now we now want to show by taking x sufficiently close to c, right? Which is, in this case, c is the 1, so that your function value minus 10 is less than the number you specified. So here's what I would do. Okay, I'm gonna do some I'll call this as the scratch work. It won't be my formal proof. So because I want this f of x minus L to be less than the epsilon that you specified. So in this particular case, that means f of x is my 4x plus 6, right? That's my f of x minus, what is the L that we think? 10. That's the limit. So minus 10. And let's simplify this a little bit. This is equal to 4x minus 4. And 4 can be pulled out, so I'm left with x minus absolute value of x minus 1. I want to show that this is less than 0.01. That's the epsilon that arbitrarily chosen. Can be any other value. Here can be any other smaller value. Now my goal is to find a delta so that as long as x is within delta range around 1, this means that, so graphically speaking, this means the following. 1 is here, center at around 1, right? And then here, this is the delta. This amount is the delta. This amount is the minus delta. So I would find you this range so that as long as x is within this range, then the y value is within the range of you specified, which is like 0.01, around 10 in this case. So now take a look at, actually, do you see that I can, so from here, I can divide both sides by 4. Therefore, I have x minus 1 less than absolute value of x minus 1 less than 0.01 divided by 4, which is 0.0025. This is actually the delta that I'm going to define. That's my delta, okay? So do you see that as long as x minus 1 is less than delta, which is less than 0.0025, this must happen, okay? And which means this must happen. F of x minus 10 is less than the number you specify. Do you see that I've done my job? Basically, what I meant is, okay, now you gave me epsilon 0.01, and you want this, your function minus 10 is less than this 0.01. I can achieve that by naming, let delta be 0.0025. In other words, if x absolute value of x minus 1 is less than 0.0025, this has to be true. Now, I know if you get lost here, sometimes a graph will be very useful. So I'm going to make a graph here to demonstrate what's happening here, okay? So I'm going to graph the f of x, which is 4x plus 6, which is a straight line. This is 4x plus 6. And I want to convince you that this is the 1. This is 10. So I want to convince you that the function that has limits 10 when x is approaching 1, right? And then you tell me how close you want the function value around 10. It's 0.01, okay? So this distance is 0.01. You want me to show you that as long as x is close to 1 enough, the y value of the function will be close to 10 within 0.01 range. And what I did was, okay, I actually found this distance, which is the 0.0025 above and below 1, when x is within this range. As long as x is within this range, all the y values are within the 0.01 that you specified, around 10. So do you see that I showed you? So let's go back to, so do you see that f of x is arbitrarily close to L, in this case 0.01 away from L, so it's close to L within 0.01 range. By making x close to C, like how close? As long as x is 0.0025 around 1, then your function value is close to this 10 within 0.01 range. So of course you say, okay, this is just 0.01. What about you take some other number? Yeah, I can always make that happen. I just need to do another algebra, just like how I did here, right? So, well, then how do we make this formal? And here's the formal definition. The formal definition says, assume that f exists for all x in some open interval containing C except possibly at C. And this limit exists if the following is true. If for any epsilon greater than 0, this epsilon is the how close you want the y value of the function to the limit L. So you specify that. Then there is a corresponding number delta greater than 0 such that the function is close to the limits within this arbitrarily chosen epsilon, within this range, whenever this happens, whenever the x is within delta range around the c. This is the formal definition, and how can you actually use this definition to prove the limits? Let's take a look at how we actually do it, okay? The first problem that we are going to prove, we actually did some scratch work on it. Now we actually prove it. So we want to prove limits of this function 4x plus 6 is equal to 10 when x is approaching 1. Now let's read this definition carefully and make sure that we are clear what we need, right? So basically, here's what we need to prove. For any epsilon that you choose, and this epsilon should be a positive number, I need to exist. That's what I want to find. There exists a delta greater than 0 such that if this x minus the 1 in this particular case, okay, 1 because the c is 1, x minus 1 is less than this delta. And what is this delta? That's my job. Here's my job, okay? My job is to actually find it, okay? Find it. And when this happens, what has to happen? Then your f of x, which is 4x plus 6, minus the limit, which is 10, has to be less than the epsilon that you provide to me, okay? So if I can do that, that's enough to conclude that the limit of this is 10. So you see that it all comes down to finding this delta. So how do I find delta? And here's again, continue my scratch work here. By the way, these are not, it's just scratch work here. So because I want to start with my targets, this is my target, okay? So that means I want this to happen, okay? By the way, what is epsilon? Epsilon is any arbitrary positive number that you choose. That's your how close you want it to be, right? So this is equivalent. So the following two are equivalent. So this happens whenever this happens. Whenever this happens, right? So we call it if and only if, using the math language. If and only if. This is just the short for if and only if. And this is equivalent to the following: 4 times x minus 1 less than epsilon. And if and only if x minus 1 less than epsilon over 4. Well, we call this as easy problem because you can see that if this happens, I want this happens, right? You can compare this with that, and you definitely can see a really nice match there. How about we just define delta to be epsilon over 4? Then when x minus 1, absolute value of x minus 1 less than this delta, which is epsilon over 4, this will happen, this will happen, this will happen. This is what we want. This is our the goal, right? So therefore, now with those scratch work, I believe I can write my formal proof, which will be pretty short, okay? I think I have to get some room to okay, I do have to erase to get some room, but you've seen the scratch work. So here's what I would write as my formal proof. This is my formal proof. So I'll say for any epsilon greater than 0, sometimes you can just say let epsilon be greater than 0. those language are acceptable. I'm gonna choose delta to be epsilon over 4. So you see, that's my job. I found it already on my scratch paper, but now I officially claim it. Let delta be epsilon over 4, or choose delta equals epsilon over 4. Then, and you have to make this happen, right? So if, or assume, if means assume x minus 1 is less than this delta, okay, delta. This means x minus 1 is less than epsilon over 4, right? That's what it means. Now, take a look at, we want to show that this has to be true. This means 4, now then we have, then, using those connecting words, then 4x minus 6 plus 6 minus 10, the absolute value sign, of course, equals 4 times x minus 1, okay? Now, here this is where this inequality comes in. Now, what is absolute value of x minus 1? I don't know, but I do know that it's less than epsilon over 4, right? So therefore, I can claim that this is less than 4 times epsilon over 4, which is equal to epsilon. Now, take a look at what we start with. This is what we have, less than epsilon. Isn't that what we want to establish? So this is what we want to establish, right? So f of x minus the limits less than epsilon, and epsilon is any arbitrary quantity that you specify. So you see that I prove that as long as I can make x close to 1 enough, this will happen. Therefore, I can conclude so. Limits x approaching 1 for x minus plus 6 is actually equal to 10. I strongly encourage you to review it. Make sure that you understand the flow of the logic, what it takes for me to conclude the limits, and how we actually do it, okay? All right, this will be a good exercise for you to try. Now, this is very much similar to this one. I encourage you to first interpret, write down what it takes for you to make the conclusion, and do some scratch work, and then write the formal proof over there. I do want to show you another different problem, which is actually a little more advanced, I would say, because it's not linear. So this time, let's take a look at how we actually prove limits of x squared when x is approaching 2 is 4. Okay. First of all, let's try to write down the according to the definition what it actually needs to prove this result. So basically, review the formal definition again. This basically for any epsilon greater than 0, okay, there exists delta, which is also greater than 0, and if x minus, okay, x minus the 2, because x is approaching 2, less than this delta, then the function value f of x, which is x squared here, minus 4, which is the limits. That means the distance between the function value and the limits is less than the epsilon, any arbitrary epsilon. So this is basically what you really want to prove, okay? Now, so here's a little, there are multiple ways to prove this problem, and here's one approach. So basically, we want to show this. I'll usually start with my target here. This is what we want to show. And the left side, we actually can factor it a little. Is that right? X plus 2. It's okay to put absolute value on both. That's what we want. And by the way, the graph of this function x squared is here. And 2 is here. And we want to show that, by the way, actually this is 4, okay? We want to show that, prove that the limit is actually 4 when x is approaching 2 from left and right on either side. But mathematically, we have to prove that formally, not just graphically, okay? Now, because we want to take x close to 2, so it's definitely reasonable to assume that, so we can assume that, suppose x is close to 2, and so that we get f of x close to L, right? So say x is in this range, okay? So 1 away from 2, which is 1 and 3. 1 and 3, okay? Suppose x is within that range. Now, what's the whole point of that? Basically, when I say that, that means x plus 2 is definitely less than 5, right? Because the highest value of this can be is 5. Can you use some other intervals? Definitely. This is really just arbitrary interval. Why do I do that? Because we want to create some certain bound. We want to bound the absolute value of x minus 2 less than something, and we have something that bothers us, which is not which is x plus 2. I want to find the maximum of this value so that I can bound. That's the whole purpose, okay? Now, and of course, at the same time, x minus 2, when we have this assumption, it's definitely less than 1, right? Because this is really equivalent to this statement, okay? So now, continue. Let's take a look at this is a really tricky one. So continue from right there. So we are talking about x minus 2 times x plus 2 less than epsilon. And we already know this guy is less than 5 based on our little assumption there, right? So therefore, do you see that this becomes x minus 2 times 5 less than, I'll say, sorry about that, let me write it better. So times x plus 2 should be less than absolute value of x minus 2 times 5, because this guy is less than 5, right? And I want this actually to be less than epsilon, okay? And therefore, x minus 2, I want it to be smaller than epsilon over 5. So that's the scratch work that I want to do. Now I think I'm ready to write the formal proof. So here's the proof. Again, keep in mind, this is what you need to do, right? So for any epsilon greater than 0, your job is to define the delta so that this is true. So proof, let epsilon be any positive number. And then I'm gonna choose, this is the tricky part, choose delta to be the smaller, which is, I'm gonna call it minimum of 1 and epsilon over 5. Okay, you may wonder why 1, because earlier when we say x, we assume x is close to 2 and it's within 1 around 2, which is x is in between 1 and 3, and which implies this guy, right? X minus 2 is less than 1. And also depending on the epsilon that you choose, x minus 2 can be some other value, can be smaller than 1, or if you choose a very large epsilon, then this guy can be larger than 1. So therefore, I'm going to choose smaller of the 1 and epsilon over 5 to be safe. So now, then this is going to happen, okay? If epsilon is greater than 5, when epsilon is greater than 5, then your delta will be 1, right? Your delta will be 1. And this is definitely, so that means your x squared minus 4, which is equal to x minus 2 times x plus 2 with absolute value sign. And this is going to be less than 1, right? And this is going to be, what do you think? X plus 2 less than 5, okay? Less than 5. And then, isn't that this is equal to 5? You see, if you choose epsilon that's greater than 5, I already showed you that as long as my x minus 2, then delta is 1, that means x minus 2 is less than 1, right? Epsilon. That's where I'm using my delta right there. So you can see that this guy is less than the epsilon you choose because epsilon is greater than 5, less than epsilon. As long as I take x closer to 2, within 1 around 2. So this is true. Now, if, oops, sorry, wrong tool, wrong pen. So if epsilon is less than 5, then your delta will be epsilon over 5. What that means is absolute value of x squared minus 4, which is equal to x minus 2 times x plus 2. And this is going to be less than, by the way, because delta is epsilon over 5, that means x minus 1 is less than delta, which is epsilon over 5, right? And I need that to bound this guy. This is how I bound less than epsilon over 5 times, and again, I assume that x is within that, so this is less than 5, which is epsilon. So hopefully that you see that this less than epsilon, when this happens, this is exactly what we want to prove. So for both cases, we prove that for any epsilon that you choose, I can always find delta. As long as this is true, this result follows. Therefore, so I can claim that limit x approaching 2 of x squared is equal to 4.